Welcome to our deep dive into electrostatics, the branch of physics that explores the fascinating world of electric charges at rest. In this video, we'll unravel the core concepts, laws, and applications that form the backbone of electrostatics. Whether you're a student preparing for exams or just curious about the invisible forces shaping our universe, this journey will clarify your understanding. We'll start with the basics, gradually building up to more complex ideas, ensuring each concept is connected and easy to grasp. Let's begin by exploring what electric charge is and why it's fundamental to everything that follows. Electric charge is a basic property of matter responsible for electric phenomena. It comes in two types, positive and negative. The quantization of charge means that charge exists in discrete packets, not in a continuous flow. The smallest unit of charge is the charge of an electron or proton, denoted as E. All observable charges are integer multiples of the elementary charge. This concept is crucial because it explains why we never observe fractions of a charge in isolation. Understanding quantization lays the groundwork for all further discussions in electrostatics. Coulomb's law is a cornerstone of electrostatics. It states that the force between two-point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. The force acts along the line joining the charges. This law helps us calculate the magnitude and direction of the electrostatic force, which is essential for understanding interactions at the atomic and macroscopic level. The constant of proportionality is known as Coulomb's constant, and the law is mathematically expressed as F equals K asterisk Q1 asterisk Q2/R2. Let's derive the expression for the force between two-point charges. According to Coulomb's law, if two charges Q1 and Q2 are separated by a distance r, the force F between them is given by F equals K asterisk Q1 asterisk Q2/R2, where K is Coulomb's constant. This force is attractive if the charges are of opposite sign and repulsive if they are alike. The direction of the force is along the line joining the two charges. This derivation is fundamental for solving problems involving multiple charges and forms the basis for more advanced concepts. Principle of superposition is a powerful tool in electrostatics. It states that when multiple charges are present, the total force on any one charge is the vector sum of the forces exerted by each of the other charges independently. This means that each pairwise interaction can be calculated separately and then combined. The superposition principle simplifies complex problems, allowing us to analyze systems with many charges by breaking them down into simpler interaction. Electric field is a region around a charged object where other charges experience a force. The electric field intensity at a point is defined as the force experienced by a unit positive charge placed at that point. It's a vector quantity, meaning it has both magnitude and direction. The concept of the electric field helps us visualize and calculate the influence of charges without direct contact, making it easier to analyze complex arrangements of charges. Electric field due to a point charge is a fundamental result in electrostatics. If a point charge Q is placed at a location, the electric field E at a distance r from the charge is given by E equals K asterisk Q/R2, directed radially outward for positive charges and inward for negative charges. This expression allows us to calculate the field at any point in space due to a single charge, forming the basis for analyzing more complex charge distribution. Dipole consists of two equal and opposite charges separated by a small distance. The electric field produced by a dipole is more complex than that of a single charge. It varies with position and direction, being strongest along the axis of the dipole and weaker perpendicular to it. The field decreases rapidly with distance, following an inverse cube law. Understanding the field of a dipole is essential for studying molecules and materials with permanent dipole moment. Electric flux is a measure of the number of electric field lines passing through a given surface. It's a scalar quantity and is proportional to both the strength of the electric field and the area through which the field lines pass. Electric flux is a key concept in Gauss's law, helping us relate the field to the charge enclosed by a surface. Visualizing flux makes it easier to understand how fields interact with surfaces in space. Gauss's law is a fundamental principle in electrostatics. It states that the total electric flux through a closed surface is equal to the net charge enclosed divided by the permittivity of free space. This law provides a powerful method for calculating electric fields in situations with high symmetry, such as spheres, cylinders, and planes. Gauss's law simplifies complex problems and is essential for understanding the distribution of electric field. Applying Gauss's law to a uniformly charged sphere, we can find the electric field both inside and outside the sphere. Outside the sphere, the field behaves as if all the charge were concentrated at the center, following the inverse square law. Inside, the field increases linearly with distance from the center. This result is crucial for understanding the behavior of charged conductors and insulators in electrostatics. Gauss's law can also be applied to an infinite plane sheet of charge. In this case, the electric field is uniform and does not depend on the distance from the sheet. This unique result is due to the symmetry of the plane, making it a useful model for understanding fields near large, flat surfaces. The uniform field is important in applications like capacitors and shielding. For a long, uniformly charged cylinder, Gauss's law helps us determine the electric field at various points. Outside the cylinder, the field decreases with distance, while inside it increases linearly from the axis. This scenario is common in wires and cables, making it a practical application of electrostatics in technology and engineering. Electric potential is the amount of work done in bringing a unit positive charge from infinity to a point in an electric field. It's a scalar quantity and provides a way to describe the energy landscape created by charges. Electric potential helps us understand how charges move and interact, and it's essential for analyzing circuits and energy storage devices. There's a direct relationship between electric field and electric potential. The electric field at a point is the negative gradient of the electric potential at that point. In simpler terms, the field points in the direction where the potential decreases most rapidly. This relationship allows us to move between descriptions of force and energy, providing flexibility in solving electrostatics problems. Electric potential due to a point charge q at a distance r is given by V equals k asterisk q. This formula shows that potential decreases with distance from the charge. The concept is similar to gravitational potential, making it easier to visualize. Knowing the potential at various points helps us calculate the work required to move charges and analyze energy changes in electrostatic systems. Potential energy in a system of charges refers to the work required to assemble the system by bringing each charge from infinity. The total potential energy depends on the arrangement and magnitude of the charges. This concept is vital for understanding the stability of molecules, crystals, and other systems where multiple charges interact. It also plays a role in chemical reactions and energy storage. When a dipole is placed in an external electric field, it experiences a torque and potential energy change. The potential energy depends on the orientation of the dipole relative to the field. The minimum energy occurs when the dipole aligns with the field, and the maximum when it's opposite. This principle is important in understanding molecular behavior and the operation of devices like electric motors. Capacitance is the ability of a system to store electric charge. It's defined as the ratio of the charge stored to the potential difference across the system. Capacitance is measured in farads F and is a key parameter in designing circuits, especially for energy storage and filtering applications. Understanding capacitance is essential for working with capacitors and electronic devices. Parallel plate capacitor consists of two large flat plates separated by a small distance. The capacitance of such a device is given by C equals epsilon asterisk a slash d, where the area of the plates d is the separation, and epsilon 0 is the permittivity of free space. This setup is widely used in electronic circuits for storing energy, filtering signals, and tuning frequencies. Energy stored in a capacitor is given by the formula U equals a half CV2, where C is the capacitance and V is the potential difference. This energy can be released quickly, making capacitors useful in applications like camera flashes, defibrillators, and power conditioning. Understanding how capacitors store and release energy is crucial for designing safe and efficient electronic systems. Capacitors have a wide range of applications in modern technology. They are used for energy storage, signal filtering, voltage regulation, and timing circuits. In power supplies, capacitors smooth out voltage fluctuations, while in communication systems, they help filter unwanted signals. Their versatility makes them indispensable in both simple and complex electronic devices. The principle of charge conservation states that the total electric charge in an isolated system remains constant over time. Charges can be transferred from one object to another, but the net charge does not change. This fundamental law underpins all of electrostatics and ensures that calculations involving charge are consistent and reliable. Materials can be classified as conductors or insulators based on their ability to allow electric charge to flow. Conductors like metals have free electrons that move easily, allowing charges to distribute quickly. Insulators such as rubber or glass restrict the movement of charges. Understanding these properties is essential for designing circuits and ensuring safety in electrical systems. Charging by induction is a process where a charged object induces a separation of charges in a nearby neutral object without direct contact. This method is widely used in applications like electrostatic precipitators and touchscreens. Induction demonstrates how electric fields can influence objects at a distance, highlighting the non-contact nature of electrostatic forces. Electrostatic shielding involves using a conductor to protect sensitive equipment from external electric fields. The charges in the conductor rearrange themselves to cancel the field inside, creating a safe zone. This principle is used in Faraday cages, which shield electronic devices from unwanted interference and ensure their proper functioning. Dielectrics are insulating materials that can be polarized in an electric field. When placed between capacitor plates, they increase the capacitance by reducing the effective field. Polarization occurs as the molecules align with the field, storing additional energy. Dielectrics are crucial for improving the performance of capacitors and other electronic components. Electric field lines are a visual tool to represent the direction and strength of electric fields. They start on positive charges and end on negative charges, never crossing each other. The density of lines indicates the field's strength. Field lines help us visualize complex charge distributions and predict the behavior of test charges in the field. Equipotential surfaces are regions where the electric potential is constant. No work is required to move a charge along these surfaces. They are always perpendicular to electric field lines. Equipotential surfaces simplify the analysis of electric fields and help in designing safe and efficient electrical systems. Work done by an electric field in moving a charge from one point to another depends on the potential difference between those points. This work is independent of the path taken, depending only on the initial and final positions. Understanding work and energy in electric fields is fundamental for analyzing circuits and energy transfer. Electric dipole moment is a vector quantity that measures the strength and orientation of a dipole. It's defined as the product of the charge and the separation distance. The dipole moment determines how the dipole interacts with external fields and is a key parameter in molecular physics and chemistry. When a dipole is placed in a uniform electric field, it experiences a torque that tends to align it with the field. The magnitude of the torque depends on the dipole moment and the angle between the dipole and the field. This effect is important in understanding the behavior of molecules and the operation of certain sensors and devices. When materials are placed in an electric field, their internal structure affects how the field behaves. Conductors allow charges to move freely while insulators restrict movement. Dielectrics become polarized, enhancing the field inside capacitors. Understanding these effects is crucial for designing materials with specific electrical properties. Dielectric breakdown occurs when the electric field inside an insulator becomes so strong that it causes the material to conduct electricity. This can lead to permanent damage and failure of electronic components. Understanding breakdown voltage is essential for ensuring the reliability and safety of capacitors and insulating materials. Capacitors can be connected in series or parallel to achieve desired capacitance values. In series, the total capacitance decreases, while in parallel, it increases. Understanding how to combine capacitors is important for designing circuits with specific energy storage and filtering requirements. Real capacitors are not perfect and may allow a small leakage current to flow through the dielectric. This leakage can reduce the efficiency of energy storage and affect the performance of circuits. Minimizing leakage is important for high-precision and long-term applications. The energy stored per unit volume in an electric field is called energy density. It's given by the formula U equals, where E is the electric field strength. Energy density is important for understanding how much energy can be stored in capacitors and other devices, influencing their size and performance. Electrostatics is not just a theoretical subject, it has practical implications in daily life. From the static cling of clothes to the operation of photocopiers and air purifiers, electrostatic principles are at work all around us. Understanding these applications helps us appreciate the relevance of electrostatics beyond the classroom. While electrostatics has many useful applications, it can also pose hazards. Accumulated static charge can cause sparks, leading to fires or explosions in sensitive environments. Proper grounding and shielding are essential for preventing accidents in industries that handle flammable materials. Electrostatic precipitators use electric fields to remove particles from exhaust gases in power plants and factories. Charged plates attract dust and smoke, cleaning the air before it's released into the environment. This technology is a practical application of electrostatics for pollution control. Modern photocopiers and laser printers rely on electrostatic principles. They use charged drums and toner particles to transfer images onto paper. Understanding how electrostatics enables these everyday devices highlights the importance of the concepts we've discussed. Electrostatic painting uses charged paint particles to ensure even coating on surfaces. The object to be painted is given an opposite charge, attracting the paint and reducing waste. This method is widely used in the automotive and manufacturing industries for efficiency and quality. Electrostatics plays a role in medical technology, such as in defibrillators and electrostatic air filters. Defibrillators use stored electric energy to restore normal heart rhythms, while air filters remove harmful particles from hospital environments. These applications demonstrate the life-saving potential of electrostatics. Let's quickly review the key concepts covered in this chapter. We explored the nature of electric charge, Coulomb's law, electric fields, Gauss's law, potential capacitance, and practical applications. Each concept builds on the previous, creating a comprehensive understanding of electrostatics. Mastery of these ideas is essential for further study in physics and engineering. Congratulations on completing this comprehensive overview of electrostatics. You now have a solid foundation in the fundamental principles, mathematical relationships, and real-world applications of electric charges at rest. In the next chapter, we'll build on this knowledge to explore current electricity and the dynamic behavior of charges. Stay curious and keep exploring the wonders of physics.